welcome everyone to the second Autonomous Climate Colloquium. Very happy to be here. Very happy to see many people here despite the exams. As many of you may know or may not know, this colloquium series is part of a initiative that runs alongside a transversal climate course that Daniel Farias and myself, Ferry Prins, are teaching. And we have many of the students here. And one of the things that we teach in the class, or that we often mention in the class, is that the textbook on climate change is still being written. And last year, spring, when we were preparing our class exactly that week on tipping points, it was a perfect example of this because right during that week, a large news cycle came out on a new article on the Atlantic tipping point, which caused an avalanche of news articles, some good, some not so good, some very much on the overly dramatic side. And this is exactly something that for us, designing this class, designing this course is so important that we, at the end, find the right way to filter the noise and actually reach, the actual experts that can explain us in a didactic and careful way what is the actual physics behind some of these very scary, at first sight, effects that are part of, the climate change that we are experiencing. So I'm particularly happy to be able to introduce Stefan Rahmstorf, who is one of the leading experts on this topic, has been working for decades on this, and is somebody who can and who takes the effort to explain these kind of complex, sometimes seemingly counterintuitive effects that we have in the climate change to the general public. So I'm not going to talk for very long. I would like to give the floor to Stefan. Just a very brief introduction. So Stefan studied oceanography at the Bangor University and did his PhD at the Victoria University of Wellington. And he then became a professor of physics of the oceans in University of Potsdam in Germany in 2000, where he has been leading a very active research line on the complexity of oceanic currents and their role in climate change. He has been lead author of the IPCC. He has appeared in many international news events to explain, the complexity of these kind of topics. And we are very honored to have you here today to give us the latest overview of this seemingly complex topic. Stefan, please.
Yes, hello everybody. It's a pleasure to be here. And indeed, as Ferry says, there is actually on this particular topic about the tipping point of the Atlantic meridional overturning circulation, a lot of false information in the media. I'm sometimes really taken aback by the relatively bad media reporting on this issue. So let's try and explain everything. And first of all, sometimes one needs to click with the mouse into that picture again if it's frozen. Oh, or the thing was switched off here. Yeah, that was the case. Okay. First problem solved. We all know this, I assume, in this audience, namely that we are witnessing an unprecedented global warming. Probably, I also work in paleoclimate for the last 30 years. The global temperature is now higher than any time in at least 120,000 years since in the Eemian interglacial, before the last ice age, but it's definitely higher than in the last 2,000 years. And yeah, we also see the reason here, and this is, we don't know this reason, namely the mainly CO2 increase in the atmosphere because of this correlation, but this was actually predicted before it was observed, because the physics behind the greenhouse effect has been clear already in the last century, no, the one before the last actually. The greenhouse effect has been known for more than 200 years. Fourier, 1824, described this as a decisive parameter for the temperature of planets. Okay, so that is the background story, but I want to focus on this part of it. If we make a map of the temperature rise, then we find that the whole globe has warmed. Around Antarctica, we don't know. This is just lack of data down there since the 19th century. But in the North Atlantic, the only part of the planet that has significantly cooled since the 19th century. So why is this? We can look at this more closely. This is the map of sea surface temperature change since 1940 in the reanalysis data. And you see a very clear cooling in the North Atlantic sea surface temperature to the west of Britain and south of Greenland and Iceland there. Actually, you see a second phenomenon, namely this bit of excessive warming here along the American coast, with a little bit of cooling to the south of it. I will get back to this because this is a linked phenomenon to that so-called cold blob that you see there. This is the latest satellite data. So since the beginning of the sea surface satellite record in 1993, that's higher resolution. You see this in nicely more detail, but again, very clear this cooling patch here and this excessive warming along the North American coast. If we look at the total ocean heat content in the top 2,000 meters, which we now know for, with pretty good accuracy, certainly in the more recent times where we have Argo floats. These are autonomous probes that are hundreds of them drifting around the ocean, diving down, surfacing again, beaming the data to satellite. So we have a pretty good picture what is happening in the top 2,000 meters. Larger error bars like before the 1990s, as you can see here, but it's clear that the total ocean heat content has been rising a lot in the last decades. And if we look at the trend picture of the ocean heat content of the top 2,000 meters since 1955, we can see again this cold blob in the Northern Atlantic. So it's not just a surface phenomenon. It considers the heat content of the whole water column. Actually, there's now pictures, data of that right to the sea bottom, which show the same thing. And the reason behind that is the so-called Atlantic Meridional Overturning circulation, which consists of a northward flow of relatively warm water going through the Gulf of Mexico, then through the Gulf Stream into the northern Atlantic, where it releases the heat to the atmosphere. The water sinks down to between 2,000 and 3,000 meters depth here, associated with deep convection because the water column gets unstable. That means the surface density is so high that so you get really deep mixing. And then that newly formed North Atlantic deep water flows southward into the Southern Ocean again between 2,000 and 3,000 meters depth as a deep western boundary current. It's kind of basic geophysical fluid dynamics. And the Gulf Stream itself was first mapped by one of the founding fathers of the United States, namely Benjamin Franklin in 1769, who was wondering why the postal ships from Great Britain took much longer towards America than the other way around. And he had a cousin who was a whaler, and he said, well, of course, this is because of the Gulf Stream. but we are just fishermen, you know, nobody listens to us. But the whalers, of course, had known this for a long time. And once the Franklin published this map, the postal ships changed their route when going to America, avoiding the Gulf Stream and sailing further south, and that greatly improved the transit time of the mail ships. Just that as a historic anecdote. Now, when you switch off this overturning circulation, you can do that in climate models, of course. The way to do it is actually to dump fresh water into the North Atlantic, which reduces the surface density enough so the water cannot sink down there anymore. This is a driving process of that overturning motion. So when you switch it off, this is the change in sea surface temperature that you get in annual mean here. Recent results from my Dutch colleagues in Utrecht, who have a nice European research grant on studying the stability behavior of the AMOC, as we call it in short, the Atlantic Meridional Overturning Circulation. And you see when you switch it off, you get this pretty shocking cooling here around Europe and over Europe. We're talking here in the range of 10 to 20 degrees Celsius. So this is massive. That is the influence that the AMOC has on the temperature. And you can see actually the whole northern hemisphere cools, the southern hemisphere warms, and that is because you are basically shutting off the heat transport across the equator from the southern into the northern hemisphere. That is dominated by the AMOC. The atmosphere doesn't do that. The atmosphere has circulation cells within each hemisphere, but the ocean can't do that because it's squashed between continents there. And so it has this great cross-equatorial heat transport, which is the reason why the northern hemisphere is generally 1 to 2 degrees warmer than the southern hemisphere at present. When you switch the AMOC off, both hemispheres get back to roughly the same temperature. So north cools, south warms, which will have important effects on the tropical rainfall belts. I'll get back to that later. Here is a schematic of the larger picture, which includes the other ocean basins. So you see the AMOC here, but you see also the deep water formation regions in orange. These are these spots here. It's the Ermanger Sea, the Nordic seas, but you also have these in around Antarctica. There it's actually forming the Antarctic bottom water, which is that purple flow going in at the bottom of the Atlantic, rising up to the level of the North Atlantic deep water and returning here. That's happening way down where the ocean is very cold and doesn't really have an influence on surface climate there. But it just shows that the Atlantic overturning is part of a larger global ocean overturning system, which exists, again, for fundamental physical principles. You can't have a stagnant ocean forever as an equilibrium state, only temporarily, with temporarily I mean for some thousand years, but there always is a kind of overturning in an equilibrium. But you can see that there is no deep water formation in the North Pacific. So this is a big difference between North Atlantic and North Pacific. And it's the reason why the North Atlantic region is much warmer than the North Pacific, and why the Northwestern European climate is much warmer than the climate in the Northwestern US and Canada. This is a kind of fancy animation of this circulation system, highly simplified. I will later show you a model simulation. You see it's rather more complex than this. It's an animation by NASA. Yeah, that kind of visualizes that part in the far north. Now, if you look at future projections, they are summarized in these IPCC reports, the Intergovernmental Panel on Climate Change, every 5 to 7 years. This is what the IPCC predicts for the year 2100. And there you see that, of course, further global warming, but cooling developing here, or actually, since we already have this cooling, getting stronger in the northern Atlantic. But these IPCC models, they underestimate what we see now, because that is the observed change per 1 degree global warming with this cold blob here. The model average, climate model average, has a bit less warming here than around it, but it doesn't actually show this cooling that is in the observation. So there is one indication that our current generation of climate models is underestimating this problem, which will, of course, be important for predicting the future. So this is what it looks like in a climate model simulation when you solve the Navier-Stokes equations in a climate model. You see here the sea surface temperature. So red is warm. You see the warm Gulf Stream coming up here along the American coast. It leaves it here at Cape Hatteras, exactly as in the real world, and starts to meander and become unstable. Beyond that, if you animate satellite sea surface temperature data, it looks exactly like this, basically, because the real ocean also has to solve the Navier-Stokes equations. It's just the ruling laws of physics here that make this happen. And if we take this climate model that I just showed you, it's from the Geophysical Fluid Dynamics lab in Princeton, which is part of NOAA, which is the kind of outfit that Trump is shutting down. So the main developer of that beautiful ocean model that I just showed you has left NOAA now for the last couple of weeks. That is a very sad development, that the top research capabilities are being destroyed in the United States now. But let's get back to what this model shows for a future scenario for sea surface temperature change. This, I should say, this is what I call the normalized sea surface temperature change. So it's divided by the global mean sea surface temperature change. So everything that's blue has warmed less than the global mean or cooled, and everything that is orange has warmed more than the global mean. And that shows you for a CO2 doubling scenario for the future, a very clear pattern. You see this cold blob, which now includes also areas that just have warmed less than the average. And it includes this funny extra warming stretch along the American coast. And you can now already see in this normalized picture that there is a blue outline here. So it's as if there is a kind of northward shift of a warm current here. And that indeed is exactly what it is. And it is part of a slowdown of the AMOC for the reasons of vorticity conservation on a rotating sphere. So it's kind of geophysical fluid dynamics. That's a bit nerdy. You don't have to understand this if you're not into geophysical fluid dynamics. But what is there to remember? That it is a well understood phenomenon from simple analytical considerations and a whole suite of models from simple conceptual to fully complex three-dimensional ocean general circulation models, that when you slow down that AMOC, that overturning circulation, the Gulf Stream here shifts to the north. Actually, the Gulf Stream also does that in the observational data. That's why in those observational pictures I showed you, there was this excessive warming in the satellite record, for example, here. And what it shows is that this is actually something that is expected from an AMOC slowdown, just as this cold blob here is expected from an AMOC slowdown. And we call this a fingerprint pattern. In this Caesar et al. Paper in Nature in 2018. And this is the trend in the observational sea surface temperature data since 1870. So it's quite a blurry picture because, of course, since 1870, we haven't measured sea surface temperatures everywhere in the ocean every year or so. So there is a fair amount of space-time averaging involved in calculating this trend. But I think you will recognize the similarity of this pattern here with what is predicted. In this case, we know in the model what it causes it, namely an AMOC slowdown. So we call this pattern a fingerprint of an AMOC slowdown in this paper. And by calibrating that with climate model data, we concluded it corresponds to about 15% slowdown of this ocean overturning circulation. And this is again from the satellite, this time also as a normalized sea surface temperature change. And here you can, by the kind of white bluish area down here, you can already kind of guess that this is a northward shift of the warm Gulf Stream that we're seeing here also in the satellite observations, which also suggests that relative to the global mean, already the waters of the UK here have been warming less since 1993, since we have the satellite data. Okay, this one I showed you already. This is the sea surface temperature trend, and there have been colleagues that have questioned whether this actually is an AMOC slowdown. Could it not be caused by surface cooling? That's why one of my bachelor students actually in his bachelor thesis has looked at the trend in the surface heat flux, and that heat loss from the ocean to the atmosphere is actually declining here, so where it's blue. So that is the opposite of a heat flux trend causing the temperature trend. Rather, it's the other way around. The temperature there is getting cooler, and that's why the ocean is losing less heat towards the atmosphere. And that kind of disproves that idea that it could be caused by surface fluxes, by maybe some atmospheric changes. It's the other way around. The ocean is ocean heat transport is declining. Therefore, the ocean is giving off less heat to the atmosphere. There's also further corroborating evidence for an AMOC slowdown in the fact that the sea surface salinity here is declining. This is it actually has the same fingerprint, this dipole pattern here, the change in salt content, the salinity declining here, increasing here. This is the corresponding time series. And in this region here, we now have the lowest salinity in the North Atlantic in 120 years of observations. And I had some discussion with the lead author of that paper, actually, who said, well, this is, she argued to me, this is all natural variability. And I said to her, are you really sure if it's the lowest salinity in 120 years and fits exactly that pattern that is just natural variability? I actually would argue that it is evidence, further evidence for an AMOC slowdown. But that's science. I mean, for every hypothesis, you get people arguing against it, and that's how it should work. That's what, in the end, makes the evidence robust. If you have argued both ways in every possible way until you come up with reliable conclusions. There are also so-called proxy data from paleoclimate. In paleoclimatology, one of the key data sources is sediment at the ocean bottom, but also the ice cores, for example. Wherever stuff accumulates over thousands of years, you can analyze the layers. There are these deposits, they give you a time sequence. And by various types of isotope analysis, etc., you can reconstruct past temperatures. And a number of different research groups have tried to reconstruct the evolution of the AMOC over the last 1,000 years or more based on these sediments. One interesting aspect is, for example, these the data, these two studies by Tornelli and colleagues, is the grain size at the ocean bottom where this North Atlantic deepwater flows over. You probably know that grain sizes under an ocean current depend on the flow speed. If it's very low, you get very fine-grained sediment at the bottom. If faster flowing, the fine-grained sediments will be washed away and you get coarse sediments. And so that's one way of reconstructing past ocean current speeds, but there are other ways as well, from isotopes, etc. And we compiled these different studies in a paper published in 21. And the general picture here is this. These studies conclude that the AMOC has been pretty stable for the last 1,000 years or more, but has been declining in the 19th, 20th century quite substantially, and is now at its weakest in the past millennium. So a few words on the impact that this cold blob is already having on our weather in Europe. This is a bit counterintuitive because the fact that the Atlantic is cold out there actually leads to more heat waves in Europe. And that is why, that is because a cold pressure system kind of likes to, a low pressure system, sorry, likes to hang around above the cold blob here. So here, this is the air pressure, and here you have a low, and that prefers to stick around above the cold water. And of course, a low pressure, you have counterclockwise air movement, and this means you get airflow from the southwest into Europe, and because of that southerly component, it brings warm air into Europe. This is a nice study from 2016. And there's a more recent one by my colleague Efi Rusi from my department, which shows that the heat wave intensity in Europe is increasing 4 times faster than at other regions at similar latitudes in the world. So Europe is a heat wave hotspot. And that may well be linked to that slowdown of the AMOC and that cold patch that is developing out to the west of Europe, out in the Atlantic. And a further study quite recently by colleagues from the Alfred Wegener Institute have shown that 14 of 18 European heat events were preceded by cold North Atlantic sea surface temperature. And so even for Spain, these changes in AMOC are already having an impact here. Another impact that we see is the more storminess in Europe. This is a study by Laura Jackson and colleagues from, it's already 10 years old now, showing that in climate models, when you slow down the AMOC, you get more winds, more extreme winds into Europe. There are further impacts of an AMOC slowdown. There's quite a bit of literature. I just recently saw a new paper on that. Is this sea level hotspot? There's on the American coast, kind of Florida up to Cape Hatteras, the US East Coast. That is a sea level hotspot, meaning the sea level there rises faster than the global average sea level. And that has been linked to the AMOC slowdown. Then impacts on marine ecosystems and fisheries still need to be explored more, but they are probably large. And then also a reduced CO2 uptake, because the ocean is now, for the last decades or 100 years, basically, it has taken up about 25% of the carbon dioxide we have blown into the atmosphere. Another 25% have been taken up by land ecosystem. That's why only half of our CO2 emissions have remained in the atmosphere. That's a so-called airborne fraction. And those 25% taken up by the ocean, they have to be transported to the deep ocean to get out of contact with the atmosphere. And there's a huge reservoir where you can store a lot of CO2 down there. But if this deep water formation declines, less of the CO2 will be taken into the deep ocean. And in the shallow surface mixed layer, which is only about typically 100 meters, you can only store very little CO2, and it equilibrates quite fast with the atmospheric CO2. And so in order to have the ocean continue to take up a quarter of our emissions, this deep water formation has to continue. And when it declines, that is bad news. Okay, that much about the slowdown of the AMOC. Now here's a nice, it was actually a very nice interactive New York Times article with interactive online graphics, warning about dramatic dangers. So what are these dramatic dangers? This is referring to the tipping point of the AMOC. And so let's talk a bit about tipping points. What is a tipping point? This is a bit of a fancy illustration of a ball sitting in like a kind of a bowl here, which is a stable equilibrium. So if you nudge it a little bit to the right there, it will roll back to its stable equilibrium. Unless you push it beyond that point there, then it won't roll back to its former equilibrium state. It will, by itself, without further pushing, move into a completely different state. And that is how the IPCC defines a tipping point, at least the physical tipping points are defined like that. It's a point from where on the system will keep moving into a new state without further pushing. And that is actually very easy to understand if I just kind of push this a bit further. There is a tipping point where it will, well, I won't show it, where I don't need to push it further so that it moves into a completely different state, namely falling off the table. So it's not rocket science. And that's why tipping points are actually all over the climate system. And the IPCC has warned that between 1.5 and 2.5 degrees of global warming, we're already very close to 1.5 now, we move into a high risk for triggering singular events or tipping points. And below 1.5, it's considered moderate risk. Above 1.5, we move into the high risk area here. And here's an overview of some of the most important tipping points of the climate system. Let me mention that there are biological and physical tipping points. The biological ones are, for example, rainforest dieback. These biological tipping points are a bit different from the physical tipping points in that they mostly refer to the limits of resilience of an ecosystem, where for the Amazon rainforest, for example, it just gets too dry for the rainforest to maintain itself, and it will then die off, burn down, etc. Or look at the coral reefs. Their tipping point already was passed between 5 and 10 years ago, mostly when the ocean waters get too warm in the summer, then the corals bleach and you get this coral die-off. And we are in the midst of a global death of the coral reefs right now, very sadly, because their tipping point has already been crossed. Okay, sorry, I'm going too fast. The ice sheets, Greenland ice sheet, Western Arctic ice sheet, they have these typical physical tipping points where a self-amplifying feedback takes over the further evolution. For the Greenland ice sheet, it's very simple. It's the ice elevation feedback. Everyone knows the atmosphere gets colder the higher you go. In the mountain up there, it's colder. And that's is very basic physics. And the top of the Greenland ice sheet is in 3,000 meters altitude, so it's very cold. But when it kind of melts down, the surface automatically comes into warmer and warmer parts of the atmosphere. And at a certain point, this self-amplifying feedback gets so strong that it takes over, and you don't need more global warming to completely melt down the Greenland ice sheet. Nobody knows exactly where the tipping point is. Some studies argue it is already been crossed, and we are already in this irreversible loss of the Greenland ice sheet. It may have already been started. If we're lucky, maybe it hasn't started yet, because if we trigger the meltdown of the Greenland ice sheet, that will take a lot of time, but it will mean 7 meters of global sea level rise, because that's how much ice there is on Greenland. Okay, now you see here also the Atlantic meridional overturning circulation as one of the tipping points, and that's what I want to discuss now. The the reason for being worried about that, when I started actually as a young postdoc in 1990, was that the paleoclimatic data showed that there had been collapse of the North Atlantic overturning circulation. And this was associated with events of ice discharge into the ocean during the last ice age. There were several of these so-called Heinrich events. And these Heinrich events, they are seen as these spikes here in sediment data in the Atlantic, where what is shown here is the proportion of ice rafted debris in the sediment. And that, what does it mean? It means like here pebbles like this that are not blown by the wind. They're too heavy for that. They're not transported with ocean currents. They are ice rafted. That means they float with icebergs out onto the ocean. And when the icebergs melt, those pebbles fall in the sediment. So the idea is you have a big North American ice sheet here in the last ice age. It flows over land. It carves into these icebergs that drift out at the bottom because it's flown over land. It takes sediments with it, these pebbles here. They drop into the sediments down here and they spread out here into the Atlantic. And this is the thickness of these ice rafted, one of these ice rafted debris layers. It's thickest here, so we know the ice must have flown in here and the icebergs floated out and distributed ever thinning layers. And so these are layers like 20 centimeters thick or so in the sediment of these ice rafted debris above and below, which is fine-grained sand. And so we know there had been these episodic iceberg armadas going out into the Atlantic. And when you look at the Greenland data about temperature and sediment data from the coast of Portugal, especially, you can see that this is associated with a major cooling there, which points to a breakdown of the AMOC, of the Atlantic overturning circulation. And the physics behind this, namely that the AMOC has a tipping point, has been known since a famous study by Henry Stommel, top American oceanographer, from 1961, where he used a very simple conceptual model where you just have two boxes, a high latitude and a low latitude box, and an overturning circulation between the two. The tipping point arises from the salt feedback. It's because the deep water in the North Atlantic can sink down there because the water is not only cold, but also salty enough. In the North Pacific, it doesn't do that because although it's colder there, it's not salty enough there to sink. But in the North Atlantic, it is salty enough to sink. Why is it salty enough? Because the AMOC brings salty water from the subtropics into the high latitudes. Water in the subtropics is very salty because there's a net evaporation region. So you evaporate more than the rainfall that goes into the ocean, making the ocean salty. And so in other words, we have an AMOC because it's salty in the Northern Atlantic, and it's salty there because we have an AMOC. That is a self-sustaining, self-amplifying feedback system. Now, if you start to dilute the salinity in the high northern latitudes in the North Atlantic by meltwater, for example, like from these iceberg armadas, then the water gets less salty, sinking slows down, less salty water is brought from the subtropics, amplifying the sinking, the slowdown of the sinking, and that now your self-amplifying feedback works the other way around into tipping the system to a switched off state. And this structure, this curve, it's actually the two-box model has as a solution a parabola. It's a quadratic function. That's the equilibrium solution. It bends back on itself, and that is the tipping point. So you start somewhere here, say present climate is here. You slowly add more fresh water. You're moving along here in equilibrium until this feedback curve bends back on itself, and this is a bifurcation point, and then you drop off the cliff. If you do it in a kind of transient, so non-equilibrium manner, as fast as the current global warming, then you're actually deviating from the equilibrium curve. You're weakening it kind of faster because we're adding fresh water fast. But then when you cross the dashed line here, that is then where the tipping point is, where it becomes self-amplifying. This has been reproduced in all kinds of models. I have one example here. This is a recent study again from the Dutch group that through this European Research Council grant, they also had fantastic computing resources occupying the Dutch supercomputer system for 6 months to do the simulation, because that's how expensive, computationally expensive it actually is. So you add this is years, but you add the fresh water very slowly. For a long time, nothing happens. And then you hit this tipping point where the overturning crashes. If you then go back, withdrawing the fresh water again, you don't go the same way. You have to go way over here until it kickstarts again. There's some overshoot here. That's a transient phenomenon. But basically, you there get back to the former equilibrium. This is what in physics you call a hysteresis behavior, and that is due to that positive feedback, the self-amplifying feedback. Now you can trigger transitions between, or let's go quickly back. If you're in between here, you have a bistable system. You have a stable equilibrium with AMOC and a stable equilibrium without AMOC. And the question is, how can you trigger transitions between the two? One is noise induced. This is again from an IPCC report, which explains the basics here. You can have a noise induced transition if you have two stable states. It's like that ball that I showed initially that is sitting in a bowl. When you wiggle it too much by some random noise, you can get over the hill and fall into the other equilibrium state. Or you can have this real bifurcation. That is when you go past that stomal bifurcation point because your background climate state has changed. In reality, so it's illustrated here on the right-hand side in a kind of stability landscape. So you could see that as a potential curve or whatever a mountain range. If you wiggle this ball enough, it can fall into this equilibrium, or you change the background state so that this one ceases to exist here, and then you fall into that different state. In reality, you will have both because we are changing the background climate change, but we're also having noise in the climate change, of course, just some random fluctuations like El Nino events and this kind of thing, decadal variability. And with this kind of system, you can, or maybe I go back here again, if you're in this state and noise will wiggle this around to some extent, now the flatter this becomes, this stability curve here, it will take longer for that ball to go back because the walls are not as steep anymore. And so this is called critical slowing down. Before you approach that tipping point, your system will not wiggle so fast anymore. It will stay longer on either side. And so people have been looking for so-called early warning signals in observational data, whether we see this kind of phenomenon of critical slowing down. And here's a nice French study on this, which is very nice because it uses very long time series. You need that because you have to look at the variance here of that variability, and you can't do that with 50 years of data. So you need longer data, really. And they use these paleoclimatic proxy data for what they call an AMV index. That means Atlantic multi-decadal variability. That is the kind of variability that is correlated with changes in the AMOC. And they use a lot of data sites here. All this whole northern hemisphere is affected by the AMOC, and wherever they find a significant correlation with the AMOC, they use these data to reconstruct this AMV index. And then they look at the autocorrelation coefficient, which is an indicator of that critical slowing down since the Middle Ages here, the year 1000. And it's been going up in the last 100 years, which is an indication of that critical slowing down of the system, and therefore for an approach of the tipping point. That's what they say in their conclusions. The AMV, you can read that as the AMOC, may now be approaching a tipping point after which the Atlantic current system might undergo a critical transition. There was another study like that using different types of data, especially the sea surface temperature in that cold blob region, as well as salinity data. Maybe that's the one that caused the headlines that you were talking about. This caused a lot of international headlines, this study, when it appeared last year. I think, was it last year? Gosh, I can't. No, it just says 23. That's already the year before last, though. That was another study which kind of suggested we are approaching a tipping point, and they actually made a linear extrapolation of the observational data here. And when this parameter lambda reaches 0, that's where the tipping point is. And they said around 2050, with a large uncertainty range that is typical for this kind of analysis, we might cross that tipping point for the AMOC. The study was heavily criticized by some other people, mostly unjustified, I thought, by people who are not really so deeply into the literature on AMOC stability. So I wrote a blog article which deals with all these criticisms. In case you're interested, you can read that up there. I personally, because the uncertainty of these studies is very large, I don't think we'll ever get a reliable early warning until it's too late. There are a number of studies that try to find early warning signs of whether we're approaching that tipping point. But yeah, we just don't have enough data, and the system is changing so fast that I think we'll be lucky to know once we've passed the tipping point, because even that is, you can't be sure because nothing drastically happens immediately. All that means is from now on, the AMOC is doomed and will slowly die. But you don't immediately see whether you're past the tipping point. We have a paper submitted in the review at the moment, which looks at the typical global warming simulations that you see in the IPCC report, except in the IPCC report, the last one that was published a few years ago, these simulations stop in the year 2100, and some groups have continued the simulations, some of them beyond the year 2100. Mind you, these simulations are very expensive. They take months of supercomputer time. That's why it's not routinely done to run them beyond 2100, but some groups that have the computing resources have done that now. And in many of those simulations, the AMOC collapses after 2100. So these are not all the simulations that have been continued, but this is a selection of those where the AMOC has collapsed. In fact, for the red ones are for high emissions. So that here are the different emission scenario. SSP 585 is a high emission scenario. So in that case, all 9 simulations that were extended beyond 2100 ended with a collapsed AMOC. For medium emissions in blue or low emissions in green, first of all, fewer runs have been done, but also only a portion of those actually collapse the AMOC, and in the majority it recovers. But what it shows that a lot of these runs in the IPCC report, which have kind of in 2100, they have between 5 and 10 Sverdrups left. That's millions of cubic meters of flow per second. A lot of them are already on the road to a full collapse. And in fact, all of the ones that have been extended that have less than 10 Sverdrup here in 2100 go on to collapse, which made us conclude that it's about, for high emissions, it's most of them for even of the ones that haven't been continued, and for medium emissions, that's still about a third or so. So it's quite a substantial risk that has been so far totally underappreciated, because many of those IPCC models apparently have already passed their tipping point in this century and are on the way to a full collapse. And it just hasn't been noticed yet because the IPCC report only shows the simulations until the year 2100. In terms of the physics, I mentioned that this deep water formation is the key ingredient here, and that is related to the deep vertical mixing. So a convection process due to the static instability in the water column in the winter, when the surface density gets so high that you can get deep mixing. That is the precursor for that whole deep water formation and the AMOC. And here is two out of these models that I showed in the last slide, looking at convection depth in the North Atlantic. And they typically have this convection here in the subpolar Gyre region, Labrador-Erminger seas, as well as the Nordic seas up here. This is a separate model. Again, they're not exactly the same, but they get it kind of pretty well right in the right regions where in the real ocean the convection occurs. And this is the time series for different emission scenarios for the different regions. So the high emissions are the solid lines, and the three colors are the three different regions here. And you see that convection collapses here round about the mid-20th or 21st century. And so that is quite a worry, because that is like 25 years away, where and we think that when the convection stops, that has its own tipping point actually, then a stable stratification forms in the water column. That is actually the tipping point that determines the future fate of the AMOC. And so we believe the tipping point based on these models is likely going to be reached around the middle of this century, and maybe even earlier if we consider that there are reasons to think these models actually underestimate this risk, because they underestimate the cold blob and various other reasons, including the fact that these models ignore actually the melting of the Greenland ice sheet and the extra meltwater that comes into the Atlantic. This model where you see the convection, that's for a low emission scenario. This does not collapse the AMOC, because the convection here gets shallower, but it continues. It doesn't break down altogether. So in this model that we see here, for the low emissions, convection continues in one side, namely the Nordic seas here, and the AMOC continues. But for high emissions, convection in all regions stops, and that's where we think the tipping point happens. And that raises the question, are there indications that the convection depth in the Northern Atlantic are in decline? That is very difficult to ascertain with observations, but there are now observational data sets compiling this, 4 of them actually, and we looked in all these observational data sets. You can see they are incredibly noisy. Some winters you get deep convection beyond 1,000 meters. That is a convection depth here. Some just a few hundred meters. It's very time variable and depends on the region. And actually those solid lines, they are fit through those dots. So you can see that's kind of these are lower smooth. It's a kind of standard way of smoothing data, but there is a lot of uncertainty. But if you look at this is 2010 here, 2020, if you look at the last 10, 15 years in all regions, in all the data sets, these curves are pointing downwards at the end. So this could be the beginning of the end of deep convection in the Northern Atlantic. But the data are too short to draw firm conclusions at this point. But it would be in line with what the models predict if that were now kind of deep convection slowly dying. And yeah, as one study that looked at the question, are the models actually too stable? This is already also quite an older one, but a pretty good study that looked at one of the standard climate models. And for standard global warming scenario run, this is the strength of the AMOC. It's going steadily here. It's a CO2 doubling run, actually. You see the blue line, it declines, but stabilizes at a weaker level. This goes for 1,200 years, that simulation. Now, these people looked at the salinity distribution in the Atlantic because that is critical for that feedback, for the destabilizing feedback. And they found that the salinity distribution deviates significantly from the observed salinity distribution. That is quite typical for climate models because it is very difficult to get the salinity distribution exactly right because it depends on a balance of rainfall, evaporation, and then the ocean currents distributing that and simulating exactly the right rainfall amounts over the North Atlantic, where you hardly have any data in the ocean, etc. That is very difficult. And so typically models are not terribly good at getting the salinity right. So what these people did is they fixed the salinity, they adjusted the salinity using observational data in the model, and then ran their CO2 doubling scenario. And lo and behold, if you have a more realistic salinity distribution in the ocean and then double your CO2, you follow this trajectory and the AMOC collapses. And so one reason why models probably are too stable with the AMOC is that they don't quite get the salinity distribution right. In addition to the fact that they ignore Greenland meltwater input. So there's actually a whole subsection of the scientific literature on this question of, are the climate models realistic in their AMOC stability? And they all suggest that probably the models are too stable. The result then, if you follow this scenario, is this kind of temperature change. You see warming. This is actually now something which is different from what I showed you earlier on. I showed you this whole Northern Hemisphere cooling. That was only shutting down the AMOC. Now you have doubled CO2 plus a shutdown AMOC. And that's why now much of the Northern Hemisphere got warmer, but around the North Atlantic, it got colder, including Britain, Scandinavia. So this would be a kind of realistic future temperature change pattern after an AMOC shutdown with CO2 increase and a lot of global warming all around it. There are more impacts, sea level change after an AMOC shutdown. I have mentioned that is already a problem. We're talking about up to 1 meter additional sea level rise compared to the global mean sea level, just in addition from dynamics in the Northern Atlantic, whereas the whole rest of the ocean gets somewhat less sea level rise if the AMOC collapses. And because of those concerns, 44 scientists presented an open letter to the Council of Nordic Ministers. I had the honor to present it at a meeting in the Arctic Circle in Reykjavik last year. And there's also this report about climate tipping points, which warns about crossing tipping points is increasingly likely at even low levels of global warming, with the time remaining to avoid such disastrous outcomes rapidly running out. And so that brings me to my conclusions. Number one, the AMOC is weakening. I would argue there's very strong evidence for that now, although not totally undisputed. The AMOC has a tipping point. I think that is pretty well undisputed in the scientific community. but it's still quite uncertain how close it is. But recent studies show that it's probably too close for comfort. We might already cross it in 25 years or so. And also similar thing is happening in Antarctica, the second deep water formation region of the global ocean, which I couldn't talk about today, but Australian colleagues have a number of studies out on that is also slowing down. With that, if you want to read more, this is an open access article in the Oceanography magazine that I wrote last year explaining this issue. And I also published those books, and you can follow me on social media. Thanks a lot for your patience, and I'm ready to take your questions. Thank you.
Hi, thank you so much, Stefan. Questions? I guess there's many. This is a difficult topic. It's not a happy story. We have a microphone here. Please go ahead. Yeah.
I was just wondering if there was any theories or ideas about how it might affect the ozone layer in the Northern Hemisphere.
I have not seen any studies on that.
Thank you very much for the talk. So you discussed that these models do not factor in the melting of the Greenland. Could you please comment on what will be the effect on Greenland, also on the collapse of the AMOC, and whether there is this again goes into a self-fulfilled feedback mechanism that accelerates the melting, or what is the general consensus on this?
Yeah, the main problem there with not considering the melting of Greenland is that this is adding fresh water to the Northern Atlantic and would increase the weakening. So the models are neglecting a factor which will be an important part of the reason for why the AMOC is weakening. What the models include is increased rainfall, which also dilutes the salinity, and increased melting of sea ice, which contributes as well. But the contribution from Greenland melting is not negligible, but it's not included in the models. Yeah, I think I'll leave it to that.
Okay. Yeah.
Thanks. So I was wondering about the consequences for Europe of the change in the currents. So usually you because of the currents you get warmer climate in Europe. So if the currents slow down, then do you expect the northern part of Europe to be colder and therefore have a greater amount of snow and ice, and that because of the increase in the albedo, then you get even colder on the northern part? Because you were mentioning that the southern part, you seem to get the more heat waves. And so do you have any predictions about what the climate is expected to look like in Europe if the AMOC slows down?
Yes, I did show one picture of that, of one simulation, but it is difficult to say exactly what it will look like, because it will depend on the balance of the warming effect of the greenhouse gases and the cooling effect of the AMOC slowdown, and how fast both things are happening, and at what point the AMOC will basically have stopped. What is the level of greenhouse gases then? So in principle, one would have to do a lot of scenario simulations to cover the whole range of combinations that is possible. And so far, only very few, surprisingly few papers have looked into this issue. But I think what is relatively clear is that in general, Northern Europe will tend to cool. How much is, depends on the balance of these two counteracting factors, and Southern Europe will warm, which means that the temperature gradient across Europe will be much larger, and that is what drives the weather, so to say. So extreme weather, especially because we don't ever experience annual mean conditions. We have sometimes warm air coming from the south, sometimes cold air from the north, and the contrast between these two will get a lot bigger, and that will probably lead to unprecedented types of extreme weather events in Europe. But how exactly is not so clear. There are the first studies coming out on impacts on society and agriculture. There's one, for example, for Great Britain on the agriculture impacts of an AMOC shutdown, and they predict a pretty massive decline in agricultural productivity in Britain. But as I said, this is kind of just starting that people are doing this type of analysis.
One second.
Well, there's just a microphone in the back. Yeah.
Go ahead.
Yeah.
Okay. Following on that question, thanks a lot for the talk. Would the agriculture productivity would be affected because of unstable climate compared to, let's say, up to now, where you have well-defined seasons, so that the humans can actually predict when to plant and when to harvest? Or would it be because of very these major events where you have crops that are destroyed because of hurricanes?
Well, I think in this case for Great Britain, in that study, it's mainly due to drying and colder temperatures. Yeah, I'm not sure actually to what extent these agricultural models can really include extreme weather events. That is notoriously difficult, even without tipping point, just for the regular global warming projections. Typically, they're kind of more looking at changes in mean climate conditions, and because it's very hard to predict how extreme weather events will change in the future.
So thank you for the talk. It looks, well, it is very catastrophic situation. So what would be, I mean, imagine that, I don't know, it could be our authority has the hope or to do something. What could be done?
Yeah, that is the most important question, of course. What can we do? And the only thing we can do is get out of fossil fuels, basically, as fast as we can. So stick to the Paris Agreement. That so there's no different conclusion from what we anyway already agreed in the Paris Agreement, except that policymakers should pursue this with much more priority than they are doing now. Because we're about to basically violate the 1.5 degrees limit in the Paris Agreement already. And so no real sign of stopping. We're still massively subsidizing fossil fuel use and things like that. So it's, I think it should just be communicated to the policymakers, which we are trying to do, for example, with this open letter to the Council of Nordic Ministers, that this is a huge risk, and we need to attach much higher priority to climate mitigation and therefore rapidly reduce emissions, because I don't think it's very feasible to adapt to the kind of situation that would arise when the AMOC crosses its tipping point.
To adapt to this catastrophic situation?
Well, at this point, one can only say that we need to increase generally the resilience of ecosystems, of agriculture, etc. But that's a fairly general statement, I know, but yeah.
Yes, thank you for the talk. You have been mainly addressing the impact of the decline of the AMOC on North America and Europe. But I can imagine, since this is a very large-scale phenomenon, it should have also some impact in the rest of the, for instance, in the Southern Hemisphere. Would you comment on that?
Yeah, the biggest impact outside the North Atlantic region would be that on the tropical rainfall, because of that Northern Hemisphere getting cooler relative to the Southern Hemisphere. That means that the latitude where the warmest sea surface temperatures are will shift to the south. And with that, the Hadley circulation and the tropical rainfall belts. And so that will cause massive problems around the tropics, because where people are counting on strong rainfall, where the rainforests are, the rainfall will decline. And where people are not used to very strong rainfall, they will suddenly get pretty strong rainfall and flooding problems.
Thank you for the talk. I was wondering, in those scenarios of the collapse of the AMOC where there are low emission scenarios, are those those scenarios related to, in the case that we respect the Paris Agreement, or just in general low emission?
Yes, I mean the lowest emission scenario, which was shown green here, that was a Paris Agreement compatible scenario.
And even so, it would collapse.
Yeah, but in most cases, it didn't collapse. I think the chance, we estimated the chance of the AMOC collapsing in this Paris Agreement scenario was like 20% or so, which is still serious risk. Obviously, you wouldn't board a plane with 20% chance of crashing, but at least it looks like if we stick to the Paris Agreement, we have a reasonable chance to avoid crossing this particular tipping point.
Thank you.
Maybe I'll ask one last question. So I think it was this week or last week, there was an article that basically talked about the recent, more frequent flooding events on the American coast, that those may already be linked to the slowing down of the AMOC. So this is perhaps one of these like early indicators, if they exist at all. So you say it's very difficult to even know if we have already crossed it. Would there be a type of event or anything that you would say like, okay, this would be the smoking gun evidence that we have crossed there? Or is it really a gray zone where we have to see what happens? I don't know.
Yeah, that study referred to the sea level rise issues. So the storm surge flooding, which indeed is that sea level hotspot along the American coast, and concluded that I think at least half of that, or around half of that, was due to AMOC slowdown. The question of an indicator of are we crossing the tipping point is actually tackled by the British research program ARIA, where they put a huge amount of funding actually into developing such early warning. My feeling, what the most promising is indeed observing deep convection in the Northern Atlantic, because as I said, I believe that when the deep convection stops, that's it, basically, that's the tipping point.
Okay. No more questions? Thank you so much, Stefan, for your talk.
Thank you.